Decompression. You're floating peacefully above Earth, sipping your freeze-dried coffee, thinking life is pretty good, and then a tiny rock the size of a grain of sand punches a hole through your spacecraft at 17,000 miles per hour. That's it. That's the whole problem. Because in space, the pressure inside your ship is the only thing keeping your blood from doing something deeply upsetting. The moment that seal breaks, the air rushes out. Not slowly, like a leaky tire, violently fast, and if the hole is big enough, you have maybe 15 seconds of useful consciousness before your brain runs out of oxygen and you become a very expensive piece of furniture. But here's where it gets weirder. If you were somehow outside the ship when this happened, say on a spacewalk, and your suit got punctured, your body wouldn't explode. That's a Hollywood lie. You wouldn't look like a balloon that met a cactus. What would actually happen is somehow worse. Your blood would start to boil. Not because it's hot, but because the pressure is so low that the boiling point of liquids drops to below body temperature. It's called ebulism, and it means your bodily fluids, all of them, begin to vaporize from the inside out. Your skin would swell up to about twice its size. You'd lose consciousness in about 10 seconds. And if someone got you back inside a pressurized environment within about 90 seconds, you might actually survive, swollen, traumatized, and emotionally unavailable for weeks, but alive. The thing that makes decompression so terrifying isn't just the physics, it's the silence. 1 second, everything is fine. The next second, the universe is trying to redistribute you across the vacuum. NASA engineers spend an almost obsessive amount of time making sure this never happens. Every seal, every joint, every tiny window on the ISS is tested to a degree that would make a paranoid person feel embarrassed about their own level of caution. And yet, astronauts still train specifically for rapid decompression scenarios, because space doesn't care about your engineering confidence. Hypoxia. Let's say the decompression is slow enough that no alarm goes off, slow enough that nobody notices. This is actually the scarier version. Hypoxia, oxygen deprivation, is one of the most insidious killers in aviation and spaceflight, precisely because it doesn't feel dangerous. It feels kind of nice, actually. Pilots who've experienced it in controlled training scenarios describe feeling euphoric, giddy, confident, like the early stages of being slightly drunk at a party where you think you're absolutely killing it conversationally. Meanwhile, your brain is running out of fuel and making spectacularly bad decisions. The terrifying part is that one of the first cognitive functions to disappear is your ability to recognize that something is wrong. So you're sitting there, oxygen levels dropping, slowly becoming philosophical threat to the mission, and you feel completely fine. Great even. You might start laughing. You might write something deeply incoherent in the mission log and feel very proud of it. In 1966, a Gemini astronaut reported that during a near-hypoxic event, his first instinct was to take a nap in space during a mission. That's the level of judgment impairment we're talking about. Modern spacecraft have redundant oxygen monitoring systems specifically because humans cannot be trusted to notice when they're slowly losing the ability to notice things. It's a beautiful paradox of engineering. We built machines to protect us from ourselves. Fire in space is not like fire on Earth. On Earth, fire burns upward because hot air rises, pulling fresh oxygen in from below and pushing combustion gases out above. It creates that classic teardrop flame shape you've seen 1,000 times. It's almost elegant. Terrible and dangerous, yes, but at least it behaves predictably. In microgravity, there's no convection. Hot air doesn't rise because there's no up. Fire burns in a perfect sphere, fed by oxygen diffusing in from all directions equally, and it burns cooler, slower, and much bluer than anything you'd see on Earth. It also burns at lower temperatures, which sounds reassuring right up until you realize that means it can combust materials that wouldn't normally catch fire in Earth conditions. Your sock, a food wrapper, the slightly damp towel you forgot about. And because you're in a sealed metal tube, fire is an existential threat at a level that's genuinely hard to overstate. There's nowhere for the smoke to go. The carbon monoxide builds up instantly. The structure of the vehicle can be compromised within minutes. The Apollo 1 fire in January 1967 killed 3 astronauts: Gus Grissom, Ed White, and Roger Chaffee. Not in space, but on the launch pad during a ground test. The capsule's atmosphere at the time was pure oxygen. at high pressure. A spark from a wire bundle ignited the interior in seconds. They never had a chance. The hatch opened inward, and the pressure buildup made it impossible to open. It was an engineering decision made without fully thinking through the worst-case scenario, and it killed 3 people in 17 seconds. NASA overhauled essentially everything after Apollo 1. They switched to a mixed oxygen-nitrogen atmosphere. They redesigned hatches to open outward. They ripped out hundreds of feet of wiring and replaced it. The whole program ground to a halt for 20 months. Space is dangerous. But often the fire that gets you was started by someone's unexamined assumption back in an office somewhere. Toxic atmosphere. You survived the fire. Congratulations. Now you might die from what the fire left behind. Burning plastics, insulation, and electrical components in an enclosed space produces carbon monoxide, hydrogen cyanide, and about 15 other gases that your body treats as a personal attack. In a spacecraft, those gases have nowhere to go. The air filtration systems on the ISS are extraordinary, but they have limits. A significant fire or a chemical leak can overwhelm them quickly. But fire isn't the only source of atmospheric toxicity in space. In 1997, aboard the Russian Mir space station, a solid-fuel oxygen generator, essentially a canister that produces oxygen through a chemical reaction, caught fire and burned for about 14 minutes while spewing smoke and metal particulates into the cabin. The astronauts wore masks and tried to vent the smoke while also being, one imagines, extremely stressed about the entire situation. And then there are CO2 scrubbers, the machines that remove carbon dioxide from the air. If they fail, and they have failed multiple times on the ISS, CO2 levels build up and you start getting headaches, confusion, then loss of consciousness. It's not dramatic, it's not explosive, it's just the air very quietly becoming poison while you go about your Tuesday. There's something uniquely unsettling about dying from bad air. At least with fire, you know you're in trouble. Bad air is the kind of problem that sneaks up on you while you're doing routine maintenance, and by the time you notice, your judgment is already compromised enough that you might not react correctly. Which brings us neatly back to hypoxia. Everything in space is connected, and most of it is trying to kill you. Radiation. On Earth, you're protected from the worst of space radiation by 2 things: the atmosphere and the magnetic field. Together, they form a kind of invisible planetary bodyguard that deflects or absorbs most of the high-energy particles flying in from the sun and from deep space. In low Earth orbit, where the ISS lives, you still have partial magnetic protection, but astronauts there still receive radiation doses roughly equivalent to 10 chest X-rays every single day, over a 6-month mission that adds up to a lifetime career limit that NASA imposes on its astronauts, meaning after enough missions, they simply aren't allowed to go back because the cumulative radiation damage becomes too significant. Go further out, though, to the Moon, to Mars, and it gets dramatically worse. During a solar particle event, a massive eruption from the sun, the radiation levels in interplanetary space can spike to immediately dangerous levels within minutes. An astronaut caught outside a shielded area during one of these events would receive a lethal dose before they could get back inside. We're talking about something that wouldn't kill you right away. You'd feel fine for a few days, then you'd start vomiting, then your immune system would collapse, then everything else would follow. Acute radiation syndrome is not a quick death. The cruel irony of space radiation is that you can't see it, feel it, or smell it. You need instruments to detect it. And by the time your instruments are screaming at you, you may have already absorbed enough to cause serious damage. Engineers designing deep space missions spend enormous amounts of time and mass budget, which is basically the currency of spaceflight, on radiation shielding. Every kilogram of shielding you add to a spacecraft is a kilogram of fuel you need to launch it. It's a constant, brutal trade-off between safety and physics. Temperatures. Space is cold, embarrassingly cosmically cold, about minus 270 degrees Celsius in the void between stars. But here's the thing, in the direct sunlight of low Earth orbit, the outside of a spacecraft can reach plus 120 degrees Celsius, and in shadow it drops to minus 160 within minutes. The spacecraft's thermal control system has to manage both extremes simultaneously, because different sides of the vehicle can be in sunlight and shadow at the same time. It's one of the most underappreciated engineering challenges in all of spaceflight. For astronauts on spacewalks, their suits do the same job. The spacesuit is essentially a wearable spacecraft, and its thermal regulation layer circulates water around the body to absorb or release heat as needed. If that system fails, If the water circulation stops, the astronaut starts either cooking or freezing within minutes. In 2013, Italian astronaut Luca Parmitano nearly drowned during a spacewalk when his suit's water separator malfunctioned and about 1.5 liters of water accumulated inside his helmet. He couldn't see. He could barely hear. He found his way back to the airlock by following the tether with his hands because the water was covering his eyes. Temperature wasn't the problem that day, but the incident showed exactly how fragile the margin for error is outside the vehicle. One malfunction. 1. Microgravity. This one doesn't kill you in a dramatic, explodey kind of way. It kills you slowly, patiently, and with a certain passive-aggressive commitment that you almost have to respect. The human body was built on Earth by evolution over millions of years in one gravity. It expects gravity. It needs gravity. Every system in your body, from your cardiovascular system to your immune function to your eyeballs, is calibrated around the assumption that there is a planet pulling on you at 9.8 meters per second squared. Remove that, and things start going wrong almost immediately. Your heart shrinks. Not dramatically, not right away, but steadily. Because in microgravity, it doesn't have to work as hard to pump blood upward, so it gets lazy and atrophies like an underused muscle. Your bones begin losing density at roughly 1 to 2% per month. Your muscles waste away. Your spinal column decompresses and you actually get taller. Astronauts gain up to 2 inches in height in space, which sounds great until you realize it also causes back pain bad enough to be debilitating. And then there are the eyes. This one, surprised, a condition called spaceflight-associated neuroocular syndrome, helpfully abbreviated as SANS, causes fluid to shift toward the head in microgravity, increasing intracranial pressure, which pushes against the eyeballs and flattens the back of them, changing the shape of the lens, degrading vision. Astronauts on long-duration missions have come back needing glasses they didn't need before. Some of the vision changes are permanent. On a 6-month ISS mission, astronauts do 2 hours of exercise every single day specifically to fight the effects of microgravity as a mandatory, medically prescribed activity, and at the end of 6 months they still come back in rough shape, pale, unsteady, needing weeks of rehabilitation to walk normally again. Now, imagine a 2.5-year round trip to Mars. Isolation. NASA doesn't advertise this one as loudly, but it is absolutely on the list of things that can kill you. Humans are not well designed for prolonged confinement in small spaces with the same small group of people, cut off from everyone they love, facing constant existential threat with a communication delay to Earth that grows from minutes to over 20 minutes each way as you travel further from the sun. There is no calling your mom for a pep talk when it takes 40 minutes to have a 2-sentence exchange. Studies of analog environments, Antarctic research stations, submarine crews, isolated habitat simulations show consistent patterns. Interpersonal conflicts escalate over trivial things. Sleep disorders proliferate. Depression and anxiety rates increase. Cognitive performance degrades. And in extreme cases, crew cohesion breaks down to a point where the mission itself becomes compromised. In 1976, a Soviet crew on the Salyut 5 space station asked to be brought home early due to psychological distress. In several simulation studies, including NASA's HISEAS habitat in Hawaii, crew members have had to be removed from the simulation due to conflict escalation. On a Mars mission, you can't abort. If things fall apart psychologically 200 million kilometers from Earth, there's no early return option. You are going to be in that tin can with those people for years, and whatever is happening between all of you has to be managed, because the alternative is a slow-motion catastrophe. This is why astronaut selection processes are as much about emotional intelligence and conflict resolution as they are about piloting skills or scientific knowledge. NASA doesn't just want people who are smart enough to go to space, they want people who are capable of being civil to someone who keeps leaving their food packaging in the wrong drawer for 2.5 years without snapping and doing something that ends the mission. Re-entry. You made it. You survived everything. Decompression, radiation, fire, bad air, microgravity turning your skeleton into something loosely resembling its former self. You're coming home. You're strapped into your capsule and you're falling toward Earth at about 28,000 kilometers per hour. And now you have to not die one more time. Re-entry is controlled, falling into an atmosphere dense enough to create friction intense enough to generate temperatures on the heat shield of around 1,650 degrees Celsius. The plasma sheath around the vehicle is so ionized that it blocks all radio communication for several minutes, a period called the blackout zone. Mission Control cannot reach you. You cannot reach them. You are alone in a fireball. The geometry of re-entry has to be nearly perfect. Too steep an angle, and you decelerate too fast. The forces exceed what the human body can survive, and the vehicle may not hold together. Too shallow an angle, and you skip off the atmosphere like a stone off water and continue into space on a trajectory that doesn't bring you back. There's a corridor, a narrow window of acceptable angles, and you have to hit it. Columbia, in February 2003, entered that corridor with foam damage to its heat shield that nobody on the ground fully appreciated the severity of. Hot plasma entered the wing. The vehicle disintegrated over Texas at 60 kilometers altitude, traveling at 18 times the speed of sound. All 7 crew members were lost. The debris field stretched across several states. Re-entry is not a formality. It is the last major way the mission can kill everyone. And you, do you think you would have survived all that? Tell me in the comments. See you soon.